All right, so we know the color of my eyes come from somewhere in my family. It's like my mom, my dad, my great grandma. What we don't know is, say I had kidney disease. We wouldn't know whether that's genetic or if it's environmental. We don't know what contributes to that. So therefore, to try to get some insight into where these type of diseases come from, there's this method called QTL analysis, which we can utilize to tap into the amazing story in the human genome, and in this example, actually the mice genome. So let's get into it. So QTL stands for quantitative trait loci, and a QTL analysis is trying to take those quantitative traits and link it to a loci. It's going to try to find a location that has a very high statistical probability of being linked to having a certain phenotype.
Let's head over to R.
All right, so right now we're just loading in our data set, which is the Lions1 CSV file from Jack's lab, which deals with gallstone susceptibility. And right now we're just going to take a look at the names of the different phenotypes, and we're going to take one that we chose, gallstone score, which is severity of gall disease, and assign it to a variable. All right, so if we take a quick look at the summary, we have 278 individuals measured, we have 15 phenotypes, and we have 97.5 of our population phenotyped. We have 97.4 of our population genotyped. We have 20 chromosomes, 19 autosomes, and one sex chromosome, and 109 molecular markers. And this is how many molecular markers we have in each chromosome. All right, so now we're going to run some quality control plots. The first one we're going to do is estimation by combination factor one, and we're looking for a really nice and purple map with no big red spots. And what this is doing is it's looking at the order of the markers and seeing how far apart they are in the chromosome. So next, we're going to map the chromosomes itself, and now we're going to map our missing data. And as you can see, we don't have much. All right, so right here is where we're going to start generating our graphs. This code is to make our main scan graph to find our probability, and we're just telling it that we want a gall score, and we're using a normal model, and we are going to use the expectation maximization method, which is just really good for data. We're going to copy this, and we're going to paste it again, and we're going to use it with 100 permutations, and this is going to give us some thresholds where we can see confidence levels.
Let's plot this to see what happens.
So we can see that there's actually a pretty big peak, which means we have a lot of confidence somewhere around chromosome 2, which we can explore further and find a more precise location. So to do this, we're going to set some threshold values, confidence levels of 63%, 90%, and 95%. And we're just going to find the location where we feel like we have the highest confidence. That's right above this red line over here. And then we can now run this to see what exactly this spot is. So now we're going to find what our highest LOD score is out of our summary. And we can just use this by doing some permutations. And then we're going to see in just a couple seconds that our highest location is at chromosome 2, at position 53.8 centimorgans with a LOD score of 3.47.